All right, so let me do a little review before we start this chapter. So you know what this chapter is about. I don't want you getting confused. There's a couple of terms that might be confusing. Okay, so you guys remember conservative forces. Okay, what are conservative forces? Okay, so the work done by any force is given by this line integral. Okay, so this is in 3D. This is the general expression, and we'll do it in 1D. Okay. The work done by a force is given by that integral. Okay. All right, so 1D in a straight line. Now, so we saw that from the fundamental theorem of calculus, if your force happens to be the derivative of a function, and the minus sign is used for convenience, the minus sign is used for physical reasons, this guy is called the potential energy function. Okay. Potential. I'm going to have to move stuff around. Energy function. Okay, so if your force is like that, so minus du by dx. So right now, don't worry about the negative sign. Remember, going from the initial point to the final point, that's the work done when this force acts and the object moves from this initial point to that final point. Okay, this is, what is this called? Integral. What is the other name? Antiderivative. So this undoes this guy. Okay, so this is equal to negative u of x initial to final. Okay, negative of u x final minus ux initial. Okay, so to calculate the work done by such a force, all you have to do is evaluate the function at the final point and an initial point. And the value is independent of how you got from initial to final point. It's independent of the path. Okay? And such forces were called conservative forces. These forces are called conservative. All right? Do you guys remember what forces are conservative forces? Okay, which ones are conservative forces? So for which force can you remember potential energy functions? I'm sorry? Spring force, very good. Spring force has a potential energy function. The potential energy function is 1/2 kx squared. Any other force? Gravity. Is that, Matthews, unlock the door.
It is unlocked. I think it just keeps kind of stuck.
Oh, I see. Gravity and the gravitational potential energy is, and we write this in terms of y because the gravitational potential energy depends on the vertical coordinate. Okay. And today we're going to talk about the third force, the electrostatic force. Okay. And we'll talk about the potential energy function for the electrostatic force. But it turns out that, so this is the potential energy function, and I'm not going to, it'll be a function of x, y, and z. Okay. What we'll do is, so this is the electric potential energy, so we'll define an electric potential function, which will be U divided by Q, and we'll come to that in a second. So that's what this chapter is about, electric potential. Okay. All right, so the electrostatic force is a conservative force, okay? And the electric field, so this is the punchline in 3 dimensions, can be written as the gradient. Do we know you?
I think we met.
Welcome back. Good to see you. Hope everything is going well.
Yeah, I just didn't know the Daytona 500 was today.
What's that?
I just didn't know the Daytona 500 was today.
Oh, I see. All right. So the electric potential is given as the gradient of the electric field is given as the gradient of the electric potential. Okay. And this is the 3-dimensional parallel of this equation. A force is given as the derivative, spatial derivative of a potential energy function. Okay. So that's what this chapter is about. Okay. And all right, so before I get into the slides, let me do one more thing. Okay. All right, here's a positive charge. What does the positive charge do? It creates an electric field all around it. Yeah. Like that. So here's an electric field. If I place another positive charge, what happens to this positive charge? I'm sorry? Right, it repels it, and so this feels a force in that direction. What if I put a negative charge there? It feels a force in the opposite direction. Okay, it's attracted. All right, so you saw an equation like this before. Force on a charge in the presence of an electric field is given by that. Okay? So if the charge is positive, the force is in the same direction as the electric field. If the charge is negative, the test charge is negative, then the force is in the opposite direction of the electric field. Okay? All right, so here's another thing. So here's the big picture that's behind this chapter. Okay. Again, now by the way, so I'm telling you a lot of independent things. We are dealing with electrostatics. What that means is the guys that are producing the electric fields, they're stationary right now. Okay? Then once we get familiar with this, then we'll get these guys to move. Okay? So right now we're keeping things simple. We are keeping these guys stationary, the guys that are producing electric fields stationary. All right. You guys understand? All right, so now let's do the following. So you have a bunch of chargers that we bought from Walmart. Yep. Well, Robert was working there because he gave us a discount.
10% off.
You can do that? All right. So, what do these guys do? They create an electric field everywhere in this room. All right. So they create an electric field. Okay. And once you know the electric field everywhere, so if you know this function everywhere, okay, this, by the way, so this is what is called a vector valued function. Yep. Ex, xy, z, I plus ey, j. Ey is a function of x, y, and z. Ez, k. Okay. All right, I'm putting out a lot of information. Okay, so you'll have to think about this carefully. Okay, so if this is a vector valued function. So you really have to give 3 functions to know the electric field everywhere in this room. Okay, why do we want to know the electric field everywhere? Now, if you put a test charge anywhere in the room, you know how it'll behave. That's what we're interested in. You guys remember shooting inkjet droplets? You shoot inkjet droplets that are charged, and if you know the electric field everywhere in the room, you know where the inkjet droplet will hit. Okay, so that's why you need to know this. Okay. So to know the electric field everywhere, you need to know 3 functions. All right, we're going to make life easier for you guys. You guys understand what I'm saying? Okay. So now if I give you this guy, what is this? See, this is a scalar valued function. That's just one function. I hope you're understanding this. What does scalar valued function mean? It just spits out a number at a location. So if I give you just this function, now you can calculate the electric field. So rather than having to give you the electric field, which involves giving you 3 functions, all I'm going to do is give you the scalar valued function and you can calculate the electric field. And that's the whole point. You guys understand? So the problem became 3 times simpler. Okay. So all that is hidden underneath the chapter. Okay. All right, so now we'll get into the slides. Hopefully you will understand what is going on. Again, we are dealing with a conservative force. The deal with conservative force is the work done by those forces is easy to calculate, because those forces can be written like so, and the work done by then is just the difference in the potential energy function. Okay. All right. And there are only 3 conservative forces that you deal with: spring forces, gravity, and the electrostatic force. We dealt with these 2 guys in physics 1. Now we're ready to talk about this guy. Okay. All right. Okay, so let's get started. So we're talking, so you will become familiar with hopefully 2 terms: electric potential energy and electric potential. Electric potential energy is denoted by U, this is denoted by V, and the 2 are related like so. Change in electric potential is change in electric potential energy divided by the charge. Okay, and you'll see why we need to define that in a few slides. Okay, so you need to be familiar with these 2 terms: electric potential energy, which is U, electric potential, which is potential energy per unit charge. Okay, so the change in electric potential is change in potential energy divided by the charge. All right. Now this is you will eventually encounter these equations. Well, if you're an electrical engineer, these 4 equations will be the basis for your life. Okay? These are called Maxwell's equations. These are differential equations. Laws of physics are expressed as differential equations most of the time. Okay? All right, so what this is saying is, okay, on the equation, the right-hand side is the cause. The left-hand side is the effect. Okay? And again, the form of the equation will be telling you the configuration of the fields and all that. Okay, what this is telling you is this is electric charge density. Electric charges produce electric fields. Okay, listen carefully. Okay, so on the right hand side is the cause, The left-hand side is the effects. Charges are producing electric fields. Okay, what this equation is telling you, so this tells you you can go to Walmart and buy a positive charge and negative charge. Okay? See, there's no magnetic charges. Well, what really is happening is you can't just go by a north pole or a south pole. When you go by a magnet, you always get them in pairs. Okay, so that's what this equation is telling you. There's no free magnetic monopole. Okay? All right, so that tells you what the magnetic field can only have certain configuration. Okay, so what this equation is telling you is the following. See, and again, you don't need to know all of this. So here's a free charge. So the divergence of the electric field need not be zero. But for a magnetic field, again, I'm giving you way too much information. Yeah. The field lines go like that, and divergence of B is always zero. Okay, that's because of the fact that you cannot go by a north pole by itself. Anyway, don't worry about it. Okay, so that's what that equation is telling you. Yeah, what this equation is telling you is the following, and we'll dedicate an entire chapter to this. What is this telling you? Can anybody read this equation? Just tell it in the language that I was talking to you about. What is the cause? Cause is time-varying magnetic fields. Okay, time-varying magnetic fields are producing electric fields. Okay, so this will be Faraday's law that we'll talk about in maybe 3-4 chapters. Okay, so an entire chapter will be based on that. All of the world's electricity, except for solar cells, is based on that equation. So there's more than $10 trillion invested in the world based on that equation. Yeah. What is this equation telling you? This is current. Moving charges produce magnetic fields. Time-varying electric fields also produce magnetic fields. Yeah. All right, so like I said, electrical engineering is based on this. So these are causes, these are effects. So what it is charges, moving charges, and time-varying electric and magnetic fields produce electric and magnetic fields. Now here's a very beautiful symmetry. Okay. So once you have produced electric and magnetic fields, if you want to detect these guys, you need charges and moving charges to detect them. So what this equation is telling you, the force on a charge in the presence of an electric field, the force on a moving charge in the presence of a magnetic field. Okay. So what we saw is you needed charges that were at rest and charges that were moving to produce electric and magnetic fields, and to detect them you needed charges at rest and charges that were moving. So this is what produces them, and to detect these guys you need those guys. Okay. So whatever is producing them is what you need to detect them. Okay. All right, that's what this equation is saying. Okay, anyway. So we will study pieces of these equations in various chapters. In one of the chapters you'll study, okay, so this is the current. So I'll just tell you one last thing about this thing. So we're just talking about this part of the equation, and I'll tell you one simple situation. So what this equation is telling you is, if you have a current like this, J is current density and I is current, it'll produce a magnetic field like this. Okay. There is the magnetic field, there is the current. So the magnetic field are tangent to the circle like that. Okay. So that's what this equation is telling you. All right. All right, now let's talk about why we have to define electric potential. Okay, so here's an electric field. So this was produced by a bunch of charges around someplace. Okay, so actually to produce an electric field like this, you will need something like this. This is a parallel plate capacitor that we'll talk about in next chapter. So let's say you smear the ceiling evenly with positive charge and you smear the floor evenly with negative charge. You will have a uniform electric field like that. Yeah. And so the electric field is uniform, it's constant, it's pointing in the same direction everywhere. All right, so if I put a positive charge here, which way will it fall? I'm sorry? Yeah, it'll fall this way. It'll fall downward. Okay, so just like, so here in this example, here's gravity. You release a mass, you drop a mass, and the mass falls downward. What is happening? The potential energy is decreasing and kinetic energy is increasing as it's falling. Potential energy is decreasing and kinetic energy is increasing. So for this positive charge, potential energy is decreasing and kinetic energy is increasing. All right, now I'm going to release a negative charge. Yeah, the negative charge falls in that direction. Okay, so in that direction, potential energy decreases and kinetic energy increases. Okay, so they fall in opposite directions. Okay, so the potential energy for positive charge is decreasing in this direction. For negative charges, it's decreasing in that direction. So we want to come up with something that's charge independent. Okay, and that is the electric potential. So we define the change in electric potential is change in electric potential energy. This is a V, that's a U, divided by the charge. Okay, and so when you define it that way, it removes the charge dependence. And so what will happen is it'll be V will be high, V is low. So this quantity, electric potential that's defined, is such that the electric field points in the direction of decreasing potential. Okay. That's why we defined that. Okay. We didn't have to define that here because there was only one kind of mass. There's not a positive and a negative mass. Okay. Here you had a positive and a negative charge, so you had to define that. Okay. All right. So the electric fields, so I'll write this down. Electric fields point in the direction of decreasing electric potential. Okay. So electric potential is high here, electric potential is here, low here. Okay. All right, so I've introduced a lot of concepts and now we'll go over them in the slides. Okay, so what is a conservative force? A conservative force is a force that is given as the gradient of a potential energy function. Okay? And the work done by the conservative force is easily calculated, U final minus U initial. Okay? That is a conservative force. What are the three conservative forces that you know? Okay, so those are the three conservative forces. And we like them because calculating the work done by them is very easy. Okay. So the concept of potential energy can be associated with conservative forces, okay? And using the concept of potential energy in conjunction with conservation of energy, one can solve problems involving varying forces. So there are some problems that are easier to solve. Yeah. All right, so we'll do some integrals for a constant electric field. So here's a constant electric field pointing this way. Again, you can create this, you'll learn in the next chapter, by smearing the ceiling with positive charges uniformly and smearing the floor evenly with uniform charges. Okay? And this is what a parallel plate capacitor. Inside a parallel plate capacitor, that's what it looks like. Okay? All right, so now what we'll have is we'll take a charge, we'll take a test charge Q naught and start here and go into that final point. So we'll take two different paths. This path, and from the same initial point, we'll take this path and there. Since the electrostatic force is a conservative force, one of the definition is the work done is path independent. Okay. So if you do this line integral, so there's the force, the work done by any force is given by this line integral. If you put a charge in an electric field, the force on the charge is Q times E. So force is given by this. Yep. And you're going to do this line integral, and since this is a conservative force, this line integral is path independent, and it's just equal to difference in potential energy. That's the definition. Yeah. And you can do these line integrals, and it turns out that the work in going from this path to this point, this line integral just works out to be that. Okay. QE dotted with D. D is this displacement. So the displacement is the displacement vector from the initial to the final point. Okay. So since the displacement vector was the same for this path and that path, the work done is the same. Okay. And you see, if the charge is positive, E dot displacement, this is positive, the work done is positive, and the potential energy decreases. Okay. So change in potential energy, so positive, so if you have a constant electric field, positive charges lose potential energy as they're moving in the direction of the electric field. So positive charges lose potential energy when the displacement is parallel to the, and when the this is positive, okay? So positive charges lose electric potential energy while gaining kinetic energy when they move in the direction of E. So positive charges will lose potential energy and gain kinetic energy. If Q is negative, if a charge falls, if the negative charge moves this way, what happens? So this guy is losing potential energy, this guy is gaining potential energy. Okay? So this is like dropping a ball in the gravitational field, this is like throwing a ball up in the air. Okay? Negative charges, on the other hand, gain electric potential energy when they move in the direction of the electric field. Yeah. So we define electric potential because electric potential energy is charge dependent. This is charge dependent, this is charge independent. Yeah. And it's only related to the electric field. So we define a potential energy per unit charge potential energy per unit charge is called the electric potential. So denoted by V, change in electric potential is change in potential energy divided by Q. So all the charge dependence falls out, okay? And there's the electric change in electric potential. This is the line integral of just the electric field, so this depends only on the electric field. Okay? So change in electric potential is negative of this line integral. All right, so now let's talk units. Potential, electric potential is measured in volts, so the left-hand side is in volts. And the right-hand side, this is potential energy, which is in joules, and that's in coulombs. So 1 volt is 1 joule per coulomb. 1 volt is 1 joule per coulomb. This also gives us a new unit for electric fields. Okay, so the electric field will be volt divided by meters. 1 volt per meter is the unit for electric fields, which was given to be 1 Newton per coulomb in the previous chapter. So this also gives us, so from this equation you can see that electric field has units of volt per volt divided by distance, volt per meter. Okay, so 1 volt per meter is also 1 Newton per coulomb. Okay. All right, so here's electric potential. Here's the change in electric potential is given by this line integral. Okay, and that's what this chapter is about. Okay, so oftentimes this line integral is hard to do, but for a constant electric field, okay, so let's say, so what this equation is telling you, so for this line integral is done when you go from here to there for this constant electric field. And E dot, if this was the displacement S, E dot S is just E times S, because they're parallel to each other. The angle between them is 0. It's just ES. So what is this equation is telling you? VF minus V initial equal to minus ES. This guy is positive. V final is less than V initial. Okay? The electric potential at this point is lower than at this point. Okay? So that's what this is. V final is less than V initial. Okay? So electric potential decreases in the direction of the electric field, or electric fields point in the direction of decreasing electric potential. Okay? So electric field lines point in the direction of decreasing potential. All right. So let's see if you guys understand this. We'll do simple pictures now. Okay, so here's a charge. Here's electric fields around this charge. So we can calculate the electric potential at this point and this point. Which point is the electric potential higher? Here or here? Yeah. So this electric potential is higher here, lower here, right? We just learned that. All right, what else did I want to point out? Okay, now, so the electric potential is higher here and there. Okay, now this is measured in volts, and let's say this is 9 volts and this is 8 volts. All right, now let's go by a proton and we'll drop a proton here. Which way will the proton fall?
Towards the 8 volt.
I'm sorry?
Towards the 8 volt.
It will fall towards here. Okay, so it'll gain velocity. Yeah. And as it falls, it gains kinetic energy. The energy it gains is called 1 electron volt. And why, we'll come to the electron volt in a second. So the change in potential energy is charge divided by change in potential. okay? The charge, it's called 1 electron volt because the charge of the proton is 1 electron. The charge of this electron, and that was 1 volt. So 1 electron volt. Okay, the proton will gain 1 electron volt when it falls through 1 volt. What if I drop an electron here? It will move toward the 9 volt, and it turns out it will gain the same amount of energy, 1 electron volt. All right, so here's what I want you to remember from today. An electron volt is a unit of energy. Very important unit of energy. And what is it? When a charge of 1 E falls through 1 volt, that's the energy it gains. Okay? And this energy is used everywhere. Okay, so let me give you an example. Okay. What did I just draw? This is a hydrogen atom. Okay. Now, if I wanted to do the following, if I wanted to take this electron away and send it to infinity, what does that mean? That means ionizing the hydrogen atom. Okay. Do you guys know how much energy is needed to ionize the hydrogen atom? Okay. So here's something you'll remember for the rest of your life. I'm going to ask you 10 years from now, 13.6 electron volts. All right. You guys understand this? Yeah.
Is that a lot of energy?
I'm sorry?
Is that a lot?
No, that's not a lot. It's very little. Okay, so anything you do in chemistry, all you're doing is rearranging an electron from one atom to another atom. So the energies involved are electron volts, 10 to 100 electron volt at best. Do you guys understand what I'm saying? So chemistry involves 10 to 100 electron volts per molecule. That's the energy involved. All you're doing is rearranging valence electrons. All right, so now we'll come to the next thing. So here's a bigger atom. I'm just going to draw a simple atom, okay? So this is this is helium, but we'll put some more. So this is a bigger atom. Now here's the deal. You just learned that to remove one of these electrons, all you need is 10 to 100 electron volts. To remove one of these guys, how much energy do you think you'll need? I'm sorry?
To remove a proton,
Yeah.
wouldn't it release energy? Since
No.
you're decreasing energy.
No. You'll need energy. So you'll need up to 100 MeV. Okay, so these are just ballpark numbers. Okay, so whenever you mess with the nucleus, the energies involved are a million times more. Okay. Okay, so to remove one proton, maybe you might need 10 MeV. Okay, so 100 million times more. That's why nuclear energy is so good.
And that's because of the strong force?
That's because exactly, that's the whole point. All right? So, soon as you start doing nuclear energy, you're talking million electron volts. Okay? Pound for pound, you get million times more energy. Okay? So whenever you mess with that, okay, so you want to remember this. Okay, so an electron volt is a unit of energy. Okay? Very useful unit of energy. Okay? And that's the energy gained or lost by a proton when it falls through 1 volt. Okay? What is a million electron volt? When an electron or a proton falls through 1,000,000 volts. Okay? Now in these units, the mass of the, you guys understanding this? The mass of the electron is 0.51 MeV. Okay, so the mass of the electron is 0.5 MeV. The mass of a proton is about 1 billion electron volts. Okay, 1 JeV. This is mass of a proton. Okay. Now, when we say mass of a proton, you multiply it by c squared, the energy equivalence of a proton. You guys have heard of Large Hadron Collider in CERN in Europe. This is a 60-kilometer circumference accelerator, and a proton is accelerated to 10 TeV, 13 TeV, which is 13,000 GeV. So they take a proton, they take two protons, and accelerate them and collide them, and their energies are 13,000 GeV. So a proton has become 13,000 heavier. So you can take this proton and hit it against a wall, and it can create 10,000 more protons. I'm loosely speaking. When you create with all that energy, what you're creating is proton-antiproton pairs. Did you guys understand that? And then they study the various forces and stuff like that, various properties of the forces. Okay. So again, so the field of chemistry is, and again, in all energy ranges, you have all kinds of stuff. Nuclear physics is in the range of 100 MeV, okay? And then particle physics is in the range of 10,000, a million MeV, so okay, 10 TeV right now. Okay, MeV is 10 to the 6, and this is 10 to the 12. Okay, so to please these guys, you just need electron volt energy. To please nuclear physicists, you need 1 million times more. To please particle physicists, you need another 1 million times more. Totally different fields. Okay. All right, equipotential surfaces. What do these words tell you? So what potential, we're talking about electric potential. Equi means equal surfaces, okay? So here's a surface where everywhere on this point on the surface, the voltage is 9 volts. That's an equipotential surface. Okay? Everywhere on this surface, it's 8 volts, 7 volts. So these are equipotential surfaces. Okay, what this diagram shows you is if you have a positive charge here and a positive charge here, two positive charges, these are equipotential surfaces. Okay? Here's a positive and negative charge, these are equipotential surfaces. And what this is showing is the electric field lines. Electric field lines are always perpendicular to equipotential surfaces. Okay? All right. Think before you answer. Is this at a higher potential or that at a higher potential? Which one is at a higher potential? This one or this one?
The one to the left.
This one is at a higher potential. Remember we said electric fields point in the direction of decreasing potential. All right. All right, so in this diagram, which way will the electric field point? This way, okay? Hello? Yeah, you can come in here. Okay. Oh, room 233. Yeah, come to the door and I'll hand you the keys. 233. My son doesn't have school today, so he's got to stay in my office. Okay. All right, so electric fields will point in the direction of decreasing potential, okay? Okay, so electric fields are perpendicular to equipotential surfaces. And they point in the direction of decreasing potential. Okay, so we'll use this to do a lab. Okay, so you'll use these 2 points to do a lab. Okay. What we'll do in lab is map these electric field lines. Okay, so this is what we'll do. We'll do next lab maybe. We'll take a positive charge and a negative charge, and the field lines around this will look like that. And this is what you'll plot, okay, in lab. You guys understand that? Okay. All right, now I'm just going to give you some expressions. Okay, I'm not going to do derivations. Okay, so here's a point charge. You guys remember the electric field from a point charge at a distance r is given by electric field is K, the Coulomb's constant, divided by times Q divided by r square, r hat. What is r hat? R hat is a unit vector pointing radially outwards from this point. Okay, so the electric field at that point is that. You just saw that the electric potential is higher here, lower there, and the electric potential from a point charge is given by K, Q divided by R. Okay. So the scalar potential, if Q is positive, the potential is positive here, okay? And if Q is negative, it's negative here, okay? So, and as you go for a positive charge, as you go further away, the potential falls. This is higher and that's lower. For a negative charge, this is a larger negative number, meaning smaller. This is a smaller negative number, meaning potential is higher, and the electric potential, the electric field points in this direction. Is my son there?
No,
Okay.
I thought.
Okay. Yeah, Matthew, you can give him the keys. What's that?
So I thought you were gonna throw it from over there.
Yeah, I didn't want to hurt him. All right, so the electric potential from a point charge at a distance r is given by this expression. Okay? And that's what this line integral does. So what this line integral is, okay, so for this you have to know spherical polar coordinates. I'll write it down, but so here's a point charge, here's point A, there's point B. Okay. What this equation is telling you is electric potential at point B minus electric potential at point A is this line integral, A to B, E dot ds. Well, this line integral, what path do you take? How do you get from here to there? Look at the answer. The answer doesn't involve any details of the path. So you can take any path you want. The line integral is path independent. That was the definition of the conservative force. Okay? So, and this electric field from a point charge is given by that. And when you do spherical polar coordinates, you learn to write this small displacement. ds, the general displacement will be r dr, small displacement radially r hat plus r, um, r, um, r sine theta d phi hat plus r d theta hat. Okay. So in Cartesian coordinates you write it like so. So that's why I'm not wanting to go over this. So this is the small displacement in Cartesian coordinates, a small displacement in the x direction, small displacement in the y direction, small displacement in the k direction. The parallel of I, j, and k are r hat, phi hat, and theta hat. Okay. And so you will learn this probably in Calc 3. And the problem is mathematicians and physicists use what they call d phi, we call d theta and all that kind of stuff. So, oops. All right, so this fella is written like so, and when you do the dot product, only r dot r survives, and you can do this line integral, okay? So anyway, so what you get is, for the difference in potential, you see you get a path-independent term, okay? So what this boils down to is, like I said, the electric potential from a point charge is given by kq by r, okay? The electric potential from a point charge at this location is given by kq by r. And that's what you want to remember. Okay. The magnitude of the electric field is kq by r square. Electric potential is kq by r. Yep. All right, so if you have a bunch of charges, you can find the electric potential at any point. You just sum the potential. If you want to find the electric potential at this guy, at this point, you find the electric potential due to this guy, due to this guy, due to this guy, due to this guy. Since they're scalars, they're just numbers, you just add them up. Okay? All right, so here are these four charges. They have calculated the electric potential at this point and all these points. And what they're telling you is, at all these points, the electric potential is 350 volts. That's what they're telling you. So what is this guy? What kind of surface is that guy called?
What is it?
Equipotential surface. See, all those names make sense.
And I guess this implies that that one point to the side that's not in the potential surface is negative and the other one's positive.
I'm sorry?
The one charge that's not within the surface is a different charge than the other three.
No, I mean, it doesn't matter. No, these four charges are the same. This is an equipotential surface. I mean, you can have an equipotential surface that's any shape. It doesn't matter. Okay. So now let me ask you this. So let's say, I don't know if this is an equipotential surface, but let's say it stands to reason it probably is. If this is an equipotential surface, which is 340 volts, which way will the electric field point?
Towards the 340.
That's right. So it'll be perpendicular to this surface, point that way. You guys understand? See, now given the potential, you can calculate the electric field everywhere. Okay? And what is the value of the electric field? The value of the electric field will be the difference in potential energy divided by the distance. Okay? So 10 volts divided by, let's say it's 1 centimeter. Okay? So that's how you calculate the electric field. And that's precisely what you'll do in the lab. Okay? Anybody remember what a dipole is? You're talking electric dipole.
When one side of the molecule is partially charged.
You're barking up the right tree, be more precise. What is a dipole? Okay, the name is suggesting that. Di, meaning two, poles. Okay, so a dipole is a positive and a negative charge separated by it. Okay. So most molecules don't have dipole moments, but if you have a molecule like this, water has a dipole moment. The oxygen atom is greedy for the electrons, and the hydrogen atoms are willing to give away the electrons. So the center of positive charge for the water molecule is there, and the center of negative charge is there. So these charges are separated, and that has a dipole moment, okay? And this is very useful. We talked about this. If the water molecule didn't have, well, if the water molecule didn't have dipole moment, life couldn't have evolved. Okay. All right, so this is really very powerful. So let's say you have these water molecules that have dipole moment. All right, now all you have to do is go make a molecule like this, which has a polar head and a non-polar tail. Okay, this is a phospholipid molecule. Okay, now if you put this guy next to this guy, what will happen? He will want to line up like this. Did you guys understand that? Why that way? Because now this is a low energy configuration. Do you guys understand that? All right. Okay, now what we'll do is we'll take here's a lake. We'll throw a bunch of these guys in the lake. Okay, so I'm not going to draw all of them, but we're going to throw a bunch of these guys in here, in the lake. What will happen? Okay, so what will happen is these guys will arrange like this. Why did they arrange like that?
Because the tails are hydrophobic.
These are, well, hydrophobic. I know that's the common terminology, but they don't hate water. It's just that this guy loves water more. So this is the lowest energy configuration. They use, so in textbooks you'll see that this is hydrophobic. This is just hydrophilic. So this is a low energy configuration. You take a bunch of these and that's what happens. So now this can be a cell. So this is the inside life, and this is the outside. So if you didn't have a polar molecule, this couldn't have happened. Did you guys understand that? All right, very powerful. Anyway, so that's a dipole. Equal and opposite charges separated by a distance. Okay, so what this is showing you is there's a positive charge and there's a negative charge. So this is the potential around the positive charge, the potential around the negative charge. Okay. So here's a dipole. The potential at this point is given by K, that's the Coulomb's constant. There's the dipole moment, P, the dipole moment is Q times D. Q is this charge and D is the distance between them. So that's the dipole moment. And you see the potential falls off as 1 over r squared. From a point charge, the potential falls off as 1 over r. from a dipole, it falls off as 1/r². Okay. So if you had a thundercloud and you wanted to calculate the potential at this point, what you do is break the thundercloud into little point charges. The electric field due to this guy, dV is K dq divided by R. And then if you want the total potential at this point, you just integrate over all the dVs. Okay. Again, this integral is impossible to do, but for very special cases. Anybody remember what is the electric field inside a conductor? Go ahead. You had it. You were correct. It's 0. Electric field inside a conductor is 0. Okay? And on the surface of a conductor, it's perpendicular to the surface. Okay, so you can take electric potential VB minus VA. So you go from here to there. If you go along, if you do this line integral, let's say you do the line integral along this path, what would you get? 0, because the electric field is 0 everywhere. You can go along this path, E dot ds will be 0 because the electric field is 0. Okay? And it turns out you could do the line integral along that path too, it'll come out to be 0. Okay? So what you find is, what we are saying is, the surface of a conductor is an equipotential surface. In fact, every point on the conductor is at the same potential. Okay? So V is constant. So you put a bunch of charges on this faucet, and every point on the faucet is an equipotential surface. And that's what this is saying. Okay? So here's a conductor, spherical conductor. That's you put a bunch of charges on it, and the charges spread out uniformly. And if you're here, the potential is there. Okay, this behaves like a point charge, and when you get to the surface, when you hit this thing, that's when the potential is that, and the potential is the same everywhere inside. Okay. So the whole thing is an equipotential object. And since the potential is not changing, the electric field inside is 0. What this is showing you is the following. Let's say you have a region of uniform electric field, and then you go bring a piece of metal and put it here. This metal alters the electric field around it because it wants the electric field to be 0 here. So what happens is charges redistribute to make sure that the electric field is 0 inside. Okay? The electric field is 0, and so it's kicked out this electric field from inside. The electric field is inside is 0, and the outside electric field got altered. Now this is not useless information. This would be the same whether this was a solid piece of metal or a hollow piece of metal. Even if it was a hollow piece of metal, the charges would redistribute such that the electric field inside was 0. Well, why is this useful? Imagine this electric field to be 3 million volt per meter. That would be creating lightning outside. And inside this metal cage, the electric field is 0, no lightning. This is called a Faraday's cage. Okay? Your car is a Faraday's cage. Okay, so here's an illustration of this. So these are metal filings that are lining up with the electric field. So inside this metal hollow, there's no electric field. Okay. So here's a metal cage. You introduce an electric field, and the charges rearrange. This end becomes positive, this end becomes negative, and the inside, the electric field goes to zero, and the electric field outside still exists. Okay. So that's called a Faraday's cage. It'll shield, a metal container will shield you from external electric fields. Okay. So for instance, if you had a building which had a lot of metal in its walls, you can't get a cell phone signal inside there. Okay. Okay, so what this shows you is the following. So here the derivation of this equation. The electric field is negative of the gradient of electric potential. Okay? Now let me, let me quickly go over the derivation, and then we really want to understand the meaning of this, okay? And I'll do an example. So here was the definition. The change in electric potential is negative of this line integral, okay? And that's equal to negative of, this line integral is really small changes in dV, okay? So small changes in dV is minus E dot ds. Okay? And so we'll do Cartesian coordinates, Ex dx plus Ey dy plus Ez dz. Okay. But from differential calculus, if dv is a function of x, y, and z, it's del v by del x dx plus del v by del y dy. Again, if you don't understand this, don't worry about it. I'll tell you what you need to understand. Okay, so this is equal to Ex dx plus Ey dy plus Ez dz. Okay, since dx, dy, and dz are independent changes, this is equal to that, this has to equal to that, this has to equal to that, this has to equal to that. Okay. So what it amounts to is the following. So here's what I want you to remember. E, the electric field at any point, is given as the gradient of the electric potential at that point. And you guys know what a gradient means, but if you don't remember it, I'm going to tell you again now. So what is this function? It's scalar valued function. Okay, so at any location it'll spit out a number. So let's say this is 100 volts, this is 101 volts, 102 volts, 105 volts. So that is the value of V at various locations. Now you can ask the question, in what direction does it increase the fastest? Okay, so it looks like this direction is increasing the fastest. And the rate of increase is given by this gradient operator. So that's what the gradient operator gives. Okay, so it gives you the fastest rate of increase of a scalar valued function. And the electric field is pointing in the opposite direction. Okay, so that's what it does. So for instance, if V, X, Y, Z is given by this function, we've done an example like this before. We're doing it again. Gradient of V is del V by del X I plus del V by del Yj. You'll do this in Calc 3, maybe. Is anybody in Calc 3? Are you guys doing it there?
Not quite. I
Not-
did a differential equations the lessons.
Okay. All right, so eventually, I mean, you will see this. So there is the gradient operator. So del V by del X is, help me out with del V by del X.
Partial derivative.
Yes, so what is it?
Well, just
2x y cubed z4. You treat the other variables as constant, okay? So when you take 3x squared y squared z4j, okay?
4x squared plus third is
Okay, so that's how you take, that's how you get the gradient. And now this, so gradient of this, negative of this is the electric field, okay? So you see, now to calculate the electric field anywhere, all you have to give is this scalar valued function. And it makes life easy. Instead of having to give you 3 functions, all you have to do is give 1 function. Okay? All right, so this is an important equation that you want to remember. The electric field is given by negative of the gradient of the potential energy potential function. Okay. Okay, so we are restating this. So these blue lines are equipotential surfaces. Electric fields are perpendicular to equipotential surfaces, and they point in the direction of decreasing potential. So electric fields are perpendicular to equipotential surfaces and point in the direction of decreasing potential. Okay? So around a point charge, equipotential surfaces are spheres, and the potential is decreasing in this direction. Here it's showing you equipotential surfaces around a dipole. Potential energy between 2 point charges is K, Q1, Q2 divided by R, the distance between them. So this is potential energy. And if you have a constellation of charges, the potential energy is the potential energy, the sum of potential energy between all pairs, between this guy, and that guy, okay? We talked about an electrostatic precipitator. If you have a smoky outfit, if you want to remove all the smoke, here's how you do it, okay? So you apply 100,000 volts. Okay, so here's metal plates, here are metal wires, and if this is 100,000 volts, what the wire will do is it'll spit out electrons, and you get these smoke particles blowing through. They will attract the electrons. Electrons will stick to them, and when they become negatively charged, those smoke particles will be attracted by these positive metal plates. So all the smoke particles can be removed. 99% of these particulate matter can be removed. Yep. And then you shake these metal plates every once in a while, and all these particles will drop. Yep. So you can clean this up. So, but to clean it up, it costs you for every $100 of electricity you produce, for instance, it'll cost you $2 of electricity. Okay, in the future, you'll all be driving an electric car. Okay, these are the numbers on an electric car. So an electric car you buy, the price really depends on the size of the battery, mostly. Okay. So for instance, everything else being the same, if you buy a battery twice as much, the price will probably be twice as much. Okay. And this size of the battery is related to the range, of course. Kilowatt hour, those are the units. So Tesla will sell you 50 kilowatt hour, and 85 kilowatt hour, and 100 kilowatt hour, whatever battery. Okay. This is the unit by which you pay your electric bill as well. 1 kilowatt hour is 3.6 times 10 to the 6 joules, million joules. And this costs you, on your electric bill, it costs you 12 cents. Okay? 12 to 15 cents. So when a 50 kilowatt hour battery is completely charged, how much electricity have you put in there? $6 worth of electricity. All right. Anyway, so if you drive this car and it discharges 60%, so you used up this much energy, 114 megajoules. That's what this calculation shows you. And in a gasoline power car, that's in liters, 50 liters. If you completely use up the tank, you used up, you get this many megajoules of energy. 114 megajoules versus 1800 megajoules. The problem is the electric car is 90% efficient, and so this is the amount of motion you got. In the gasoline car, which is 20% efficient, this is the amount of motion you got. So for a 60% discharge, you got this much motion, and for a 100 full tank of gas, you got 3 times as much. Okay. That's what those numbers are telling you. All right, guys. This was a long chapter.